Hello students, so today we will study chemical kinetics theory part 1. So, disclaimer, the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concern or issues, please contact us at sathee@iitk.ac.in. We shall remove the images. So the topic for today's class are, first of all, the rate of a reaction. Second is rate law and rate constant. Then we will study order of reaction, molecularity, differential and integral forms of differential order reaction, that is for zero order reaction. Then we will just do the summary part. So first of all, let us study about the rate of a reaction. So what is the rate of a reaction? So basically, the rate of a reaction is you can think of it as similar to the rate or speed which you have studied in physics. Okay, so you must have studied to calculate the speed of a moving object. So similar to that, we try to analyze the reaction with their speed or rate or velocity. So this thing is called as speed or rate of reaction. Now, in when we are talking about the say our moving body, we what do we analyze? We analyze the distance covered per unit time. But in case of a reaction, we don't have any distance or something like that. So we have a thing which is analogous to this distance, which is our say change in concentration of reactant or product. Okay, and the time thing is remain same. Okay, time is remain same. Okay, now, so what do we say overall? So we can say that the rate of a reaction or a speed of a reaction or a velocity of a reaction, anything we can refer to, is the rate of change of concentration of reactant or product in unit time. So the thing here is to keep in mind is that you should be able to analyze the rate of reaction with the help of reactant and the product both. Okay. So suppose we have a reaction, we are going from A to B, then the rate of a reaction can be defined in two ways. Okay. So the two ways are the average rate of reaction first of all. Okay. So this is the average rate of reaction. So you may look here that the formula is written as change in concentration of A divided by change in time with a negative sign. Okay, I will tell you the significance of a negative sign. First of all, let us see the complete formula. So then it is written as in terms of product. So initially it was in terms of reactant, and now in terms of product it is written as change in concentration of B with respect to time. Okay, clear? Now here one thing is to notice is that why we are putting the negative sign. So I mentioned it earlier. So this thing is given because to keep the say your rate as positive value, means the rate of reaction should be always positive. Why? So you must have never seen that a speed or something like that of an object can be negative. It is not possible, right? So you can use the same analogy here also, that the average rate of reaction or any rate of reaction can never be say negative. So to keep that sign convention good, we put a negative sign against this expression. Okay, so and how do we get a positive value? Very clear, we are going from A to B, so the concentration that is of reactant is decreasing, so the final must be smaller than the initial. So final minus initial will give you a negative value, then negative multiplied by a negative will give you what? It will give you a a positive value overall. Clear? Okay, now moving on to next thing. Okay, so similarly in terms of product we can write the same thing, that's delta B by delta T. Now why are we saying it at average rate of reaction? So in average rate of reaction, the thing that is important and it should be noted, that we are using the delta word. The delta word is a kind of change, but this change is referred to a larger change. Okay, so we use the term delta for that. So we are observing our reaction for a longer interval of time, so for that case the average rate of reaction is used. Okay, this then the second one is what? So the second one is to look upon the units. Okay, units of the rate of reaction, average rate of reaction. So you can see here that it is written as mole per liter work per second. It is very obvious. Now the concentration is written in terms of mole per liter, so this is nothing but your molarity. Okay, and then divided by delta T, so time, that is per second. Now it can be written in mole per liter per minute also, but the SI unit will be mole per liter per second. Okay, clear? So unit should be clear to you. So very simple. Change in concentration will have a unit of mole per liter, and since second is in upon, so we will put it on the upside and do the sign as -1. Okay. Now the next thing is the instantaneous rate of reaction, which is represented by R with the subscript INST, that is a short form or abbreviated form of instantaneous. Now how it can be calculated? Very simple. Just look at that formula we have seen earlier, and what we have done is that we have limited the time change almost to zero. So what do you mean by this? So you must have seen this in your calculus also. So when we are limiting the time to delta t, that means the change in time is almost negligible or close to zero. Okay, it is almost negligible and close to zero. Okay, now we can represent this as how? We can represent it as minus dA by dt. Okay, or in terms of product, dV by dt. Clear? Okay, very good. So what is the difference in formula of both of this instantaneous and average rate of reaction? So in average rate of reaction, we were using the delta, okay, and in instantaneous rate of reaction, we are using the word D, sorry, the letter D. Now the difference is only that we are limiting the time, okay, to a small change. Okay, we are here we are saying that it is for a larger interval of time, then we are saying it as average rate of reaction, and when we are representing for a smaller time interval, then we are using dt. Clear? Okay. Now yeah, one more thing, the unit will be same for both of them. Okay, so rate of this unit is good for both of them, so you can use it for either average rate of reaction or for instantaneous rate of reaction. So this is in general. Now the general reaction, which is written as, suppose we are taking a reaction which is going from A plus B to X plus Y, and their corresponding coefficient are also written with the smaller letters. Okay, so if suppose we are saying that the reactant A is reacting, it is represented as capital A, then its coefficient is represented by the smaller version of that letter, that is small a. Okay, it is just a general representation of common reaction. So in that case, what will be the rate of reaction? So here the rate of reaction which is written here is the instantaneous rate of reaction. Why? Because we are again using the small time. So this dt means small time always. Okay, so you must have heard this also in case of, say, your calculus, that we are differentiating something, and for differentiation we use small time, small intervals. So in this case we are using small time intervals. Okay, now how do we write this? So in this case what we do is that, so what we are writing here is that change in concentration of A with respect to time, and what else we are doing apart from the negative sign, we are also dividing the whole term by the coefficient. So suppose we are writing in terms of we are writing the rate of reaction in terms of reactant A, then we are dividing it by the coefficient of the same reactant, which is small a. Similarly, for reactant B, we are dividing it by small b, which is the coefficient of the reactant B. Okay, similarly same goes for the X and same goes for the Y. Only the thing is to notice, again I am repeating it, that you have to put a negative sign when we are writing in terms of reactant, and we have to put a positive sign when we are writing in terms of product. Clear? Okay. Now next we will see what are the factors that affect the rate of reaction. So this thing, that why do we study factors? Okay, why it is important? So whenever we do a reaction, right, we want to control the rate of reaction. So suppose you are doing a reaction, and the product is very required in your daily life, and but the reaction is going slowly. Okay, but you want the reaction to go a bit faster. Okay, or the reverse can also be true, that you want the reaction to prolong laster. Okay, so how do we change it? How can we change or alter the rate of reaction? So for that, we have to look upon the factors that affect the rate of reaction. Now, by alternating these factors, you can change the rate of reaction and get your desired product. Okay, and that time can be also be changed with controlling these factors. Clear? Okay. So first factor is the rate of reaction, which depend upon a number of factors. The first factor is concentration. Okay, so first is concentration. So it can be either of the concentration, means it can be of the product or reactant. So we can change the rate of reaction by changing the concentration of reactant also, or by introducing the product also. Clear? Second is nature of reactant. Of course, if we take different reactant, we will get different product, and also the rate of reaction will change. Okay, so this is very obvious. Next is temperature. Temperature has a very large play to role for any reaction. Okay, so you must have studied this in equilibrium also in class 11, that we use this temperature to change the, say, your product concentration by varying the equilibrium constant, right? Okay, whatever. So coming back to this thing, it is very important. Okay, temperature changes the rate of reaction. Now we will see how does it changes in the later on sections. Then the fourth thing is your presence of catalyst. Okay, so catalyst, obviously catalyst is used to enhance the rate of reaction. So if you want to do a reaction, if it is going slower, or else you are finding it difficult to complete the reaction, then what do we use? We use catalyst to enhance the rate of reaction. We will see that how this rate of reaction is enhanced with this catalyst. Clear? Okay. Next is your exposure to radiations. Okay, what is exposure to radiations? So radiations can be of either type. Okay, it can be of either type. What do you mean by that? So you can either say you can introduce some light, artificial light, your UV or something like that, or you can use the sunlight. So both of this can change the rate of reaction. So there are many examples of reaction which are photochemical reactions that do get altered with the help of your radiation exposure. Your simple example would be, so you must have seen the dissociation of Cl-Cl bond in the presence of light, that is used for the chlorination of simple alkanes. Clear? Now we'll study about the rate law and the rate constant. Now, according to law of mass action, we know that the rate of chemical reaction is directly proportional to the product of effective concentration of reacting species. Okay, each raised to a suitable power which may or may not be equal to the respective coefficients. Okay, stoichiometric coefficient. Now what do we know, what do we get about by the idea about reading this? So we get an idea that, okay, that we have a reaction. Okay, we have a reaction. Now the rate of that reaction is directly proportional means if you increase the product concentration, okay, if you increase the product concentration, you will see that the rate of reaction has increased. So that is the main meaning of that. Now, how fast or what amount of change will alter how much the rate of reaction, that will depend upon the power. Okay, so here it is written also that each of this concentration of product is raised to some power, to a suitable power. Now this power is say experimentally determined. Okay, now this thing is very important here. We will use this concept in the later on say coming slides also, and you will use this in the questions also. It's the main point throughout the, say, your chemical kinetics chapter. You will see to and fro the use of this word, that the power should not be equal to stoichiometric coefficient, the power should not be used for the stoichiometric coefficient. Okay, so this should be always in your mind. Okay, now there are cases which is in that case their stoichiometric coefficient and your say power is same, so that case will be mentioned in the later on slides. But till now you should keep in mind that this power to which the product concentration is raised is experimentally determined. Clear? Now consider a general reaction. Suppose we are having, similarly, we are taking a general reaction in which we are reacting reactant A with reactant B, and the reactant A is having a coefficient which is equals to small a. So we are taking a variable, any variable you can take. You can write here x also or small a also. So similarly for B, we have written it as small b, and when we react, these two are getting our product. Clear? Now the rate can be written as, how? The rate can be written as K multiplied by concentration of A raised to the power alpha, concentration of B raised to the power beta. Okay, so this equation that you are seeing here, this equation is called what? This equation is called your rate law. Clear? This is called a rate law. And you can see very clearly that I have not written here A and I have not written here B. Okay. So I have written here a different variable which is alpha and beta. So this alpha can be equal or not equal to A. Similarly, this beta can not be equal or not equal to B. So that depends upon the reaction and many more factors we'll see in the later on slides. Now what is K here? So this K is nothing but your rate constant or velocity constant or specific rate constant. So why are we saying specific rate constant? So this specific word is introduced whenever we change the concentration of both the reactants to unity. Okay, so when we do so, so if we keep this concentration of A as 1 and concentration of B as 1, then your rate will be equals to rate constant. So that is the reason we are saying it as specific reaction rate. Okay, so whenever you must have seen the same thing, or if you will study electrochemistry also, you will see this, that your specific resistance. So when we do the area of cross section of as 1 and your length as 1, you get the resistance as a specific resistance. So it is clear to you. So similar to that, when we are changing the concentration to 1, or we are keeping the concentration of reactant as 1, then we get the rate constant equals to your what? Equals to your rate of reaction. For that reason, it is called a specific reaction rate. As I have told you earlier, so this is called as what? This is called as rate law. Next. Now, as I have told you, so this alpha beta, which we have seen it in the previous slide, which was our, say what, it was our power to which the reactant was raised. So this was said that it can or cannot be equal to the stoichiometric coefficient. Okay, so it was said earlier. So keeping that thing in mind, we can say that we cannot deduce the rate of reaction. Okay, sorry, we cannot deduce the rate law. Okay, we cannot deduce the rate law from Balanced equation. So if you are able to do so, then you don't need this experimental value alpha beta. But since we said that earlier very clearly that your stoichiometric coefficient are not always your power, so we can say that we cannot get our rate law from the Balanced equation. Clear? It is obtained experimentally. Okay, so as mentioned earlier, we have seen this definition also. So why do we call a specific rate constant specific reaction rate? Because the rate constant is defined as the rate of reaction when the concentration of each reactant is taken as unity. Okay, so when we take the concentration of each reactant as unity, then the rate of reaction is equal to the rate constant. Next is, what is the unit of K in this case? What will take the unit of K? So for that, let us again see the rate law. So in this case, we are only taking one reactant. So suppose there is a reaction, a general reaction which has only one reactant, which is A. Okay. For that case, we can write rate is equals to K multiplied by concentration of reactant A raised to the power n, again to some power which may or may not be equal to the stoichiometric coefficient. Now for this case, okay, for this case, what we can do, we can just put all the units of the, say, terms that are being displayed here. So for rate, we have put upon mole per liter per time. Very simple. Okay, we have seen it earlier. It can be mole per liter per second or mole per liter per minute, depending upon the reaction that we are dealing with. Okay, so we are determining it for K. So we have written it as it is. For A, what we can write, since A is the concentration term, so and we are using the molarity as concentration. So the unit of molarity is mole per liter, and its power is small n. Okay. Now we can say that K is equals to how much? So we can write, you can just work it out. It's very simple. Just work it out. So here mole has a power of 1, here mole has a power of n. So when it will come downwards, it will be 1 minus n. Means mole will have a power of 1 minus n. Liter will have n minus 1, and s, since we don't have a term here for your time, so it will remain as it is, which is per second. So we have used the second unit as for time. Okay, so this should be kept in mind. So we have replaced the unit of time with second. Okay, so don't get confused. Next is, what is here n? Okay, so what is n here? So this is very important. So if you have gone through the chapter of, if you have got also introduction, then you must have seen this term, which is n, and it is what? It is your order of reaction. Okay, what is n here? This is your order of reaction. Now let us see more about this order of reaction. So what is order of reaction? So what we do is that we simply add the powers that we are seeing on the rate law. Okay, we simply add the power that we are seeing in the rate law, and upon adding the power, whatever we get, whatever the value we get, that is called the order of reaction. Okay, whatever is we get, whatever we summed up is called the order of reaction. Clear? So what again I am repeating it. So take the rate law and see what are the powers that is being put upon the reactant concentration terms. Add all of those powers and you will get the order of reaction. Okay, consider a general reaction going from a plus b to x plus y. So we have again taken the equation. You must have seen it earlier also. This is general equation. Okay, now how we will write the rate? So according to law of mass action, we can write the rate as dx by dt. So it is where dx by dt is simply rate, is equals to k times the concentration of A. So here A and B are reactants. So we have written A here, reactant A raised to the power A, and reactant B raised to the power B. Clear? Okay. Now, but according to rate law, what we will write? So according to rate law, we will write dx by dt. So we know that this is for law of mass action. Okay, this is for law of mass action. So it is used in equilibrium. But for rate law, we can't write the same thing, as I've said it, mentioned it earlier also. So we have written here alpha, which may or may not be equal to A, and here beta, which may or may not be equal to B. So summing up this, we can write dx by dt equal to k concentration of A raised to the power alpha, B raised to the power beta. So for this reaction we have written. Now, what will the order of reaction? So we have discussed it multiple times. What we will do is we will simply add these two powers of reactant, that is alpha plus beta. So this is your overall rate of or overall order of reaction. Okay. So this can be only determined experimentally. Why? Simple, very simple. So since these powers are determined experimentally, so their sum can also only be determined experimentally. Okay, so this is very obvious. Next important thing is your molecularity. Okay, next important thing is your molecularity. What is molecularity? So molecularity is defined as the number of ions or molecules taking part in an elementary process of the reaction mechanism. Okay, what again? I'm repeating it again. What is molecularity? It is the number of ions or molecules that are taking part in an elementary process of reaction mechanism. Why are we saying it elementary? So for that we have to see an example. So we will see the example later on. For now, remember this thing, that this is nothing but the number of ions or molecules that are taking part in an elementary process. Now, in case of simple reaction known as elementary reaction, molecularity is simply the sum of molecules of different reactants as represented by balanced equation. Okay, what are simple reactions? So simple reactions are those reactions which takes place in one step. Okay, you get my point? Suppose a reaction is happening, and how it is happening? Two reactant molecules are reacting, or say you will see in the collision theory that for reaction it will collide. So what are they doing? They are reacting, and there is no intermediate or something like that, and you are directly creating a product. Okay, now for those reactions, we do calculate molecularity by simply adding the number of molecules that have reacted or that have collided to get the product. Okay, and this simple reactions are called what? This simple reactions are called elementary reactions. Okay, so I have told you earlier that what we do, we calculate the rate of molecularity of reaction by taking the elementary process and adding the number of ions. So this is the definition of elementary reaction, in which the reaction the reaction is taking place in one step, and there is no intermediate involved in that reaction. Now let us see some examples. So suppose we have one molecule and that is getting dissociated into 2 moles of NO2. Okay, so we are taking N2O4 and that is getting dissociated into 2 moles of NO2. So since in the reactant side we have only one reactant, 1 mole of molecule of reactant, so we will tell it as unimolecular reaction. Again, another example, what are we taking? We are taking the dissociation of HI. So what are we doing? We are taking HI and what are we doing? We are decomposing it or dissociating it into two molecules of H2 and I2 respectively. Now in this reaction, what do we see? On the reactant side, we have two molecules. Okay, see here, two molecules. Since 2 is the coefficient that is used, so we can say that this is a bimolecular reaction. Now next is trimolecular reaction. Again, remember the point that all of these reactions are elementary. Okay, so this is happening in one step. There is no intermediate involved. Next is trimolecular reaction. In trimolecular reaction, what will happen? 2 moles of NO will react with 1 mole of NO2 and we will get 2NO2. Okay, what will get? We will get 2NO2. Clear? Is this thing clear? Okay. Now, here you can see 2 moles of NO and 1 molecule of O2. So 2 molecules of NO and 1 molecule of O2. So total will be 3 molecules. So for this reason, it is a trimolecular reaction. Again, this reaction is taking place in one step. It is an elementary reaction. Now, what about complex reaction? So see, one reaction is taking place in one step, so it is called elementary. If that reaction involves multiple steps, suppose we are reacting 2 reactants, they are giving us a third reactant that is reacting with a fourth reactant. So you got my point. We are not directly getting the product. There are intermediates involved. So in that case, molecularity has no meaning. Okay, so for a whole complex reaction, molecularity has no meaning. So what do we do in that case? So for that case, we consider the elementary reaction. Now, as I have told you earlier, that your stoichiometric coefficient can or cannot be equal to the order of reaction. Now we will see the case when the order of reaction is equal to the what? Your stoichiometric coefficient. So we will say that if we have an elementary reaction, then your order of reaction is your what? Your equals to the stoichiometric coefficient. Okay, so that thing is very important to remember. Now in case of complex reaction, what do we do? What is the order? In case of complex reaction, we take the slowest step, and whatever will be the order of the slowest step will be the order of what? Will be the order of your overall reaction. Clear? So for complex reaction, order is calculated how? It is calculated with the help of the slowest step, and it will be equals to molecularity of that reaction. So since we are doing a reaction in multiple steps and we are taking the slowest step, and that is elementary reaction again, so the molecularity of that reaction will be equals to the what? Equals to the order of reaction. Now suppose we have a reaction which is this reaction, okay, which is going in multiple steps. The first step is HbRO3 plus Hi giving us HbRO2 plus HiO. In the second step, what will happen? HbRO2 will react with again more HIs and you will give you HBr plus 2H2O plus 2I2. So this is the first step. And in the third step, this HiO will again react with Hi and will give you H2O plus I2. Clear? Okay. Now, all of these steps are elementary steps of a single reaction, of a single complex reaction. So, what do we do? For the overall reaction, how we will calculate the order? We will simply take the slowest step, calculate the molecularity, it is 2. So this reaction follows the second order kinetics. As simple as that. You have nothing to worry about. If you have a complex reaction, take the slowest step, calculate the molecularity, and that will be your order of reaction. Now the thing here is to notice that now the order of reaction can be changed with conditions such as pressure, temperature, okay, but molecularity does not change. So this is very, very important thing to remember. So it is very obvious also. So what is molecularity? It is the number of molecules that are colliding to give a reactant. So that will be fixed. Okay, if you want a reactant, you can't just take one molecule of Hi and give the reactant. You will need HbRO3, or either it will violate your law of mass of action. So that is very important. Now order can vary. Okay, order means the rate of reaction will vary with your concentration of Hi. So we know that. So how fast or how slow it can vary, that can depend upon the pressure, temperature, that will depend. I will not say that will depend upon the external conditions. So that can be pressure, temperature, or concentration also. Next important thing that is to be noticed is that molecularity is always a whole number. Okay, so why is it so? Because you can't take a fraction molecule, you will take a full molecule. Okay, so that can be 2 molecules, 3 molecules, it cannot be 2.5, 3.5. Okay, it is not possible at all. Okay, this is not possible. So it can never be zero, because you can't react your no molecule and get a molecule. It can never be negative, because molecule can never have a negative value. Okay, counting can never be negative. Next is fraction. Okay, fraction, as I told earlier, you can't take a fraction of molecule. Whereas order can be anything. It can be zero, it can be negative, it can be fractional, anything. Okay, it can be negative also, right? So this is very important, that the order of reaction may be negative also. Let us now see the differential rate of equation and integral rate of equation. So what do you mean by this for a zero order reaction? So reaction in which this can react. What is zero order first of all? So we have talked about order of reaction. So when we keep the power of the concentration of product, so means the sum that we are taking, we take it as zero, then the order of reaction become the zero order of reaction. Okay, means there will be no effect of what, of changing the concentration of reactant. Whatever you do, it will not change the what, it will not change your overall rate of reaction. So what are we doing? Okay, one thing very important, that is what are we doing with this rate law? So we have seen that there are multiple factors that affect the rate of reaction. So we are now studying the reactant thing. Okay, we are looking upon the reactant, that how does reactant concentration change the order of reaction. Okay, or the rate of reaction, sorry. So what are we looking upon? The factor, we are looking upon the concentration factor, that how the concentration factor can change the rate of reaction. Okay, anyways, coming back to the zero order reaction, we have taken a common reaction. Say we are going from R to P. So the differential rate can be written as, so why are we saying a differential rate? Because we can see that we are using a differential from minus dr by dt. Again, we are using the reactant thing. So for rate law, since we are using the reactant term on the right side, so accordingly we'll take the rate differential form of reactants only. Clear? So this is the differential form, and we are getting it as k multiplied by r raised to the power 0, because it is a zero order reaction. Now the integrated rate equation will be given as how? So it will be given as k is equals to minus within brackets we will write c t, that is concentration at time t, minus c naught, which is initial concentration, by time t. Okay, this is your integrated. So what we have done, we have taken this equation that we see here and we have integrated it, and upon integration within proper limits, we get this equation for the integrated rate equation for the zero order reaction. Again, I mentioned it earlier, c naught is the initial concentration, ct is the concentration at time t. Next is half-life of a reaction. Okay, what is half-life? Half-life is nothing but it is the time. So we are taking half-life, what? Half-life as the time to make the initial concentration half of the initial value. Okay, sorry, to make the concentration, not the initial concentration, to make the concentration half of its initial value. Suppose we started it with 8 moles per liter. When the concentration goes to 4 mole per liter, then the time that has been used to take the concentration from 8 to 4, so what we have done, we will half it. So that time is called the half-life of the reaction. Clear? Again, I am repeating it. So it is the say time that is required to change the concentration to half of its initial value. So if you write it for zero order reaction, what it will be? It will be simply T half is equals to C naught by 2K. Very simple. So you have seen the equation earlier, that your K is equals to minus Ct minus then within bracket Ct minus C naught by K. So what we have done, we have changed the concentration to half. So in place of Ct, what we have written is C naught by 2. So so we can say that your final concentration is half of your concentration is half of your initial concentration. So we have written C naught by 2 for Ct. Okay. So and for T we have written as T half. So since we are calculating half life, so we have written T is equals to T half. So you upon putting all these values, we get it as C naught by 2K, where K is what? Again, your rate constant, and T half is a half life period. So half life of a reaction or half life period, both are same. So what we can deduce from this equation, that for a half life, okay, for half life of a zero order reaction, it is this half-life is directly proportional to C naught. What is the meaning of this? So what the meaning is very simple. So if you take initial concentration, suppose you are taking 8 moles per liter, okay, then you get your first T half, and you then take 16 moles per liter, then you get your again another T half. So the second T half which you get will be larger than the initial T half, and the reason is what? Because you have taken a greater initial concentration. Clear? Got it? Okay. Now what about the unit of K? So very simple. Just use this general equation, put n is equals to 0, and you will get this thing. So if you just look at it here also, okay, just simply put the unit of all of this, you will get the unit of K. So for C naught, it will be mole per liter. For time, it will be per second. You can put it in this either equation. Either you can put it here, or you can put it in the back equation. Okay. So since 2 is a constant, it will have no unit. So you will get the unit as mole per liter per second, which is simply your what? It is simply your unit of rate of reaction. Now covering up all of the thing that we have studied till now. So first thing is the rate of reaction is what? It is simply how, the measure of how fast or how slow the reaction is getting converted into product. And what is rate constant? So rate constant is the frequency of effective collision, okay, between reactant molecule. What is the order of reaction? So it is simply the addition of your reactant reactant concentrations power, okay, for a given rate law. And what is molecularity? It is the number of molecules that are colliding together to give your product, okay, in the elementary reaction. Okay, so this was for today's lecture. Thank you.